Ammeters and breadboards. How do they work? So we're going to use a gauge, a breadboard, soldering iron, some wires, some resistors, and some batteries. And we're going to set up a circuit using the breadboard and find the current going through the circuit using the gauge. At the end, we're going to provide detailed explanation of how a breadboard works as well as how an ammeter works. So first we begin by soldering the wires onto the contacts on the back of the gauge.
So now what we have is our 9-volt battery, our 1.5 volt AA battery, and a 3-volt mercury battery. So, and we also now have 4 of our 470,000 ohm resistors.
Oh dang.
Look at that. So here we go. So we got our 2 wires here, positive to positive. And then, as I try to make contact, I did see it twitch. Maybe I need to switch it. And now.
Are there too many
There you go,
resistors?
there you go.
So, how many microamperes is that?
What you got? 60.
That was alright.
Using 470,000 ohm resistors, all in parallel. So, that was the 9-volt. Now we will try and see what happens when we use the 1.5 volt.
So, which battery are we using now, Andrew?
The AA 1.5 volt battery.
Ooh.
There we go. It sort of moved a little bit. There. So, with the 1.5 volt, we have 11 microamps.
You know.
What do you know?
You know.
And again, with 470,000 ohm resistors.
Woo.
And now, finally, our 3-volt mercury battery. Look at it go. The mercury battery has 21 microamperes. Wow. Now, how exactly does this breadboard work? How is it possible that we can make a complete circuit where the wires seem to be in no way connected at all? Well, underneath inside of the breadboard, there are many connections. The dots here on this diagram represent all the inputs on the breadboard, and then the lines represent on the inside of the breadboard the connections between those inputs. So as you can see with the diagram, for each of these sections, each of the 5 inputs for each column are connected to each other. So like these 5 are connected, and then the next 5 are connected, and the next 5, and the next 5, and the next 5, and so on throughout the entire thing. Now, there's also the power input and grounding. Now, these strips are connected the entire length, unlike the columns here, where this and these 5 are connected to these 5, and then connected to these 5, and so on throughout this entire row. And then the same thing with the grounding. So if you were to connect power into here, and then connect some component there, there, and there, they would all receive power because these are all connected. And then the same thing with grounding. If you were to connect this wire to ground, and then you have other wires going into here, 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 any of these, then those would also be connected to ground because they would share this common connection with this wire going to ground. Now, for placing components on the board, typically what you would do is you would put one end of the component into this section, and the other end into the component into this section, as we have done here with these resistors that we use for the experiment. To show you on the diagram, what this would look like is you have a resistor with one end into this input, like so, and then the other end into this input. And in doing so, what you do is you connect this column to this column when before they were otherwise not connected. And if you were to connect another resistor, say in series, what you would have to do is you would have to connect one end of the. There's a couple ways to do it. What you would do is you could connect one end of the resistor to the next column over, say here, and then what you would do is you would take that, come up here, and then you would just connect it to the column that the other resistor is on, like so. And in doing so, now you have them in parallel, with the condition being that power is only inputted into the second column here and not this first column. So to get power to those resistors, what you'd have to do is you'd have to take this power strip and you'd have to get what's called a jumper, similar to what we have right here, where it's just a simple wire connecting the power to the column that you're using. So what you do is just take a wire and connect it like that, input to input, right there. And now this column has power, and because it's powering this resistor going to here, this column gets powered, and then it goes through this resistor, and then we get to here. But now it's not connected to any ground. So to connect it to ground, all you have to do is the same thing you did for connecting power, is you just have a jumper that goes from the powered column to the ground, to the row where all the ground is. And then there you go, that's basically a complete circuit.
Ammeters are devices that are used to measure current. They can be digital, like the ones you've seen in class, or analog, like the ones you see in this video. While not all analog ammeters are built exactly the same, they all usually function off the same basic principles and ideas in order to measure current. In this general case of an analog ammeter, we will consider one that has an iron core and a needle, with the iron core surrounded by wire, as shown in red, and a spring connected to it, as shown in green. Now, as we learned early in the semester, we learned that a magnetic field can create a torque on loops of wire, and that a torque, as in 220, creates an angular acceleration, which results in a changing angle, which results in rotation. Now, the torque from a magnetic field on a loop of current is given by mu cross B, where mu is the area of the loop times the current running through the loop. Now, in these cases, it is not just mu cross B that satisfies this situation. Instead, it is N times mu, because you have N loops of wire on the iron core. The more loop you have, the more torque you will generate. And when you simplify this equation out, you get the given equation, N times A times I times B times sine theta. Theta being the angle between the B field and the area vector of the loop. Now, we don't want the iron core spinning forever. So that is why the spring is attached, so that way we have something to stop it and keep it stable so we can measure how much current is actually running through the ammeter. Now, from our 220 days, let's remember that torque is equal to F cross R, and when the force is coming from a spring, it is given by this formula, where force of the spring is equal to the spring constant K times delta S, the displacement of the spring, essentially how much it is stretched. Now, the loops of current will keep rotating and keep stretching the spring until when the spring is stretched out just enough, the torque of the magnetic field will equal the torque of the spring. Now, if we substitute the equations that we have and solve for I, we can easily find out that depending on how much your needle moved, how much current is going through it. It is important to note that at the numerator, the sine phi is simply the angle given by F cross R. So the angle between the force and the distance vector applied. Ideally, this would be something like 90 degrees, but it is up to the user. Something important to note here is the last part of this equation, the denominator, which, as shown, is the theta final. This theta final is actually given by the equation theta initial, which is the initial angle between the B field and the area vector, plus the delta theta that you get when the needle moves. This delta theta can be easily related to how much the needle moves, and therefore, in the appropriate areas and with the appropriate numbers, you can mark the ammeter with however much current can go through it, depending on your choice of spring, number of turns, magnetic field strength, and other constants.